Hello and welcome to Psyched Up! Before we get started, I think we should talk. I know that many of you have had a difficult history with math. You're brave for being here. Stats is scary. It's built on top of calculus, trigonometry, and linear algebra. These are dangerous things, not meant for mortal minds, which is why we won't be doing any of that. So let me start by saying that this topic is completely conceptual. When I talk about reading, understanding, interpreting, and extrapolating, there's a reason that calculation isn't on the list. We're aiming to be informed consumers of science. You can think of it like literature. You don't have to be a master novelist to understand why Toni Morrison is a freaking genius. Yeah, she is. So we'll be focusing on the different kinds of tests and what they mean, and more importantly, what they don't mean. Bad science hurts my heart. We'll also look at the different kinds of graphs that are thrown around and how to avoid falling for the tricks that misrepresent data, because bad reporting on bad science hurts even more. But today we're going to look at the basis of why we even use statistics in psychology by looking at how probability works. A single coin represents a 50-50 chance of coming up heads or tails. But what if I, say, get 3 heads in a row? Or 5? Am I more likely to get a tails? Well, let's say that is the case. What does that mean? Is the head stored in the coin or in me? If I switch coins, does it reset? If I bury the coin for a year and don't flip anymore until I dig it back up, am I still more likely to get a tails? Spoiler alert, it doesn't actually matter. Every coin flip is exactly 50-50, even if I flip 10 or 100 tails in a row. This mistake in our intuition is called the gambler's fallacy, and it happens when we mix up the two key kinds of probability. Coin flips fall under independent probability. That means that none of the results influence each other. As you might have guessed, the other side is dependent probability. That means that if you know one result, you'll be better at guessing the next one. Can you think of an example of dependent probability? Common one is the weather. If it hasn't rained for a week or two, and you don't live in LA, then it's probably going to rain soon. And if it's been raining for the past hour, it's probably still going to be raining in the next hour. And if it's been raining for 4 days, then you'd be right to guess that it's going to stop raining soon. But you wouldn't always be right. And those mistakes are called error, or noise. And noise is what makes probability so important for science. If we're dealing with a dependent probability, then the error is systematic. That's bad. We often don't know how to correct for systematic error, and so our predictions get messed up. We'd rather have random error, because if we can make that assumption, then we can rely on it canceling itself out. To see how that works, we'll change from coins to dice. Let's start with just one. Dependent or independent probability? Just like coins, it's independent probability. Let's see what that looks like. Here are the possible rolls, 1 through 6, and here's the chance of each roll happening. Every number is always equally likely to happen as every other number. Here's what 2 dice look like. Why isn't it flat? Well, here's where I'm going to have to break my promise about no math, because we need to do some addition. How many combinations can make a roll of 2? Just 1, snake eyes. A roll of 3 can come from a 1 and a 2, or a 2 and a 1. A 4 comes from a 1 and a 3, a 2 and a 2, or a 3 and a 1. If we do that for every number, we get this pyramid shape. So are 2 dice still an independent probability? Yep, a dependent probability just means that one roll can predict the next roll. If I roll a 5, I am more likely to roll a 6 or a 7, but that's just because I'm rolling 2 dice. I'm always more likely to roll a 6 or a 7. The rolls before and after don't matter. And an independent probability means random error. So back to that canceling out idea. Every low number has a partner high number with an equal chance of happening. That means that if we roll enough dice and take the average, we'll always end up at or around 7. The normal curve and its ability to cancel itself out is super important in psychology. So the next video in this series will be all about that normal curve, no numbers. I promise. Next week, we'll start our series on psychology in the media. We'll take what we know as good consumers of science and look at what the article does well or does poorly and what we can do to improve it. You can check back next week or subscribe to stay up to date on all of my videos. Until then, have a great week, friends!